Let's look at a famous probability puzzle called the Monty problem. So you are on a game show with 3 closed doors, and behind one door there is a car, and that's the prize you're interested in. And behind the other 2 doors there are goats. So that if you open those doors, the idea is that you lose. And so you choose one door, but the door is not opened yet, right? And then the host of the program, who knows what is behind each door, opens a different door and shows you a goat. And so now there are 2 unopened doors left, your original choice, and one other door. And the host asks you whether you want to stay with your original door or if you want to switch to the other unopened door. And the question is, should you switch, right? And one of the key things here that's very important is this fact over here, that the host knows what's behind each door. So he's not randomly opening a door. He is always going to open a door that has a goat behind that, right? And what we'll see is that because of this fact, since you have this extra information, you can actually improve your odds by switching. So essentially what will happen is switching is going to double your odds of winning. And so this is, many people are generally very surprised about this. And so let's analyze this problem carefully. So without loss of generality, let's say you selected door 1. And you can just call whatever door you selected, call that door 1. And then let's call door 3 the door that the host opens, revealing the goat, right? And so what we are interested in, let's start by defining some events here. So if we define CI to be the event that the car is behind door I, and if we let H be the event the host opens door 3, showing goat, then what we want to find, what we want is we would like to find what's the probability that the car is in door 1, so let's say the door that we chose, given that the host opened door 3. And we want to compare that with what's the probability that it's in the other door, given what the host did. So the idea is we want to update our probability about the car given the new information that we got, right? And like we saw, how do we update information here? We use Bayes' theorem, right? So we're going to use Bayes' theorem to look at something like what's the probability that the car is in door I given what the host did. It's going to be the probability that the host opened his door, did what he did, by the conditioned on the car being in CI, times the probability that the car is in door I, and divided by the probability of the host doing what he does. Okay, so to compute this, we need to have the priors, right? And then we need to be able to have these conditionals here. And we saw this one, you can just compute it from the law of total probability if you have all expressions of this kind. So let's do this. So if we start with the priors, so what are the prior probabilities? That is the probabilities before we see anything. Well, we are assuming that essentially we don't know anything about where it is, and so the probability of it being behind any of the doors in the beginning of the game is the same and is equal to 1/3. So the probability, so when the game starts, if you don't know anything, the probability of the car being anywhere is going to be 1/3. And now we also need the conditional probabilities. So let's compute these. So what is the probability that what's the probability that host opens door 3, right, if the car is in 1? So if the car is in door 1, then that means that there are 2 goats in door 2 and door 3, and so he could open any of them. And so we're going to give a half chance of him opening any one of those 2 doors, right? Now, what's the probability that the host would open door 3 given that the car is in door 2? Well, that means that since we selected door 1, that means that we selected the door with a goat, and now door 2 has the car and door 3 has a goat. And of course, we know that the host always opens the door with the goat, so that means that here it has to be probability 1. If the situation had happened that we chose the wrong door, then it's with probability 1 that the host is going to open the door 3 with the goat, because he can't open the door with the car. Now, what about the probability that the host opens door 3 given that the car is in door 3? Well, that can't happen because he will never open the door with the car. And so you see that this is sort of capturing that information that the host knows. Since the host knows where the car is and he's never opening that, in the case where we haven't selected the car, well here actually, yeah, so the case here where we haven't selected the car, it's sort of determined what he will do from his point of view. He's just going to always choose the door that the other goat that we didn't select, right? And so now with this, we are interested in computing the probability that the car is in door 1, given that the host opened door 3. And so we saw this is going to be the probability that the host opens the door 3 with the goat, given that the car is in door 1, by the probability of the car being in door 1, divided by the probability of the host opening the door. And so this bottom part, we saw we can open it up by the law of total probability. So the probability of the host opening door 3, we can open it in terms of all the possibilities for the cars. So this will be the probability that he does what he does, given that the car is in door 1, by the probability of the car being in door 1, plus the probability that he does what he does, given that it's in the door 2, the car, by the probability of the car being in door 2, plus the probability that the host opens door 3 with the goat, given that the car was there, times the probability of car 3, right? And so now, if we compute these, so h given c1 is half, times c1 is going to be 1/3, plus h given c2 is 1, times c2 is going to be 1/3, plus probability of h given c3 is going to be 0, times 1/3. And so if you add this up, you will get a half here. And so now we can go back and substitute. So h given c1 is half. Probability of c1 happening is 1/3. And we divide this by half. And so this will give us the probability of it being there is going to be equal to 1/3. And now there are just two choices, it's either in C1 or C2 because he opened the second door. See, he opened the third door, so then 2/3 has to be the probability that it's in the second door. But for completeness, let's actually compute that. Let me write these, let me make space for that. So if I delete this over here, and let's say I write these next to each other. Let's actually compute it explicitly. So what's the probability that the car is in door 2, given that he opened door 3 with the goat? Again, this is the probability that he did what he did. He opens the door 3 with the goat, given that it's in C2, by the probability that it's in C2, divided by the probability of him opening the door with the goat, which we computed, it's the same one under. So h given C2 is equal to 1, and then times 1/3 divided by half, and so this will be equal to 2/3. And so you can see here that if he were to choose the second door, so if you change the door, so he knows, the contestant, if you decide to choose the second door, you will have a 2/3 chance of winning as opposed to the one you chose before, right? And so switching doubles your chance of winning. And the key point is that the host did not open a door at random without information. The host knew where the car was and intentionally revealed the goat. And so that action gives you information, and conditional probability helps us account for that information correctly.